Hello and welcome to the course project presentation for cloud computing. We are the Deduplicating Cloud Functions team. Our project was carried out under the mentorship of Shripad Nadgowda, who is a senior researcher at the IBM Research Center, and Professor Oran Krieger. Our project team includes Belis, Paritosh, Vikas, and Ashutosh. Our entire project focuses on deduplicating the cloud functions in serverless platform. So why is serverless platform so hot these days? Serverless provides a new, unique way to build and run applications without having to manage infrastructure. This means that for software developers on the cloud platform, we no longer have to worry about how does our application scale or how do we manage the infrastructure. Rather, we can focus more on the logic of our functions. Let's understand the working of the serverless platform on an intuitive level. Imagine that we have a cluster of IoT devices whose sensors are constantly generating some sort of data and putting in a data store. We also have some analytics dashboards that are constantly generating data and putting it in the data store. Now, as a software developer, you have written a lot of functions that use the data present in the data store and run it on the serverless platform in the form of stateless functions. Now imagine these stateless functions are generating some output, for example, generating metrics that what sort of data is coming in from the sensor data, or sending emails when some sort of event is happening in one of the sensors, etc. Now, what if the data that comes into the data store is duplicate? In that case, stateless functions that are being executed are redundant. Imagine this on a large scale where the data that is coming in comes in for every second, and we are executing these functions again and again for the same data. Nowadays, most cloud vendors charge you based on the number of times your functions are executed and the duration for which the function executes. But what if we could reduce the number of executions itself? So this is what sparked the idea for our project. Now imagine a scenario where we have the same cluster of the IoT devices generating the data constantly, and we have the same analytics dashboards that are generating the data. Now, when a unique data comes into the data store, we execute the functions. But in case of when the duplicate data comes into the data store, we are no longer computing the functions again. We are rather returning the outputs from the data store itself. So the scope for our project is not to deduplicate the data, but to deduplicate the invocation of the functions themselves. This means that the input data, which is duplicate, will still need to be stored into one of our cloud object storage, but we would deduplicate the invocation of the cloud functions. Our framework is built on top of OpenWhisk, which is a serverless platform. We have chosen OpenWhisk since we needed a platform whose internal architecture was completely open and for which the documentation was readily available. Since we needed good results for our proof of concept, understanding the internal working of the serverless platform was really essential. So the aim for our project is to develop a function deduplication framework for serverless platform as mentioned earlier, and the users for this framework would be the cloud users who use the serverless computing and the cloud vendors themselves. How does OpenWhisk work exactly? All the commands that are submitted using the Whisk CLI against the OpenWhisk framework are nothing but simple HTTP requests that enter the Nginx reverse proxy server. These requests are then forwarded to the controller, which is implemented in Scala. This controller acts as the main interface responsible for all the actions the user can perform. The controller then authenticates and authorizes the user. It checks the CouchDB if the user is present and if the user has the privileges to perform the actions that he's trying to achieve. Once the user is authenticated, the controller then loads the code for the action from CouchDB itself. Once the code has been successfully loaded, the controller then refers to console. Console is responsible for letting the controller know which one of the invokers is available to execute the action. Once this information is available to the controller, The controller sends the action to one of these free invokers via Kafka. Once the action reaches the invoker, a custom Docker container is spinned up. Inside the container, the action is executed. Once the container is done with executing the action, the output is stored in CouchDB. Now, in a case where your code or the action itself has a lot of library dependencies, OpenWhisk requires you to write a custom Docker image and push it to your Docker Hub registry. While creation of your action, you need to specify the location of this image, which will be pulled while spinning up this container. Now let's have a look at the architecture of our Sanity framework. Here we can see that we have made use of the Minayo Cloud Object Storage. Now this is an S3 compatible object storage. Then we have used the Kafka, which is a log processing agent. We use this to trigger the events whenever a new data comes in to the Minayo buckets. We have made use of CouchDB to store the references of the output that OpenWhisk generates corresponding to the unique data. Now let's assume a new data comes into one of the Minayo buckets. Whenever a put event happens in the Minayo bucket, Kafka notifies Sanity controller a new data has come in. Then Sanity computes the checksum of the data. It then checks the CouchDB for a ref hash of the function. If the hash is present, it then checks whether the hash of the input data is present in CouchDB. If the hash is present, it checks if the output reference of an output is present in the CouchDB. If all these three conditions are satisfied, then we can conclude that the data that just came in is a duplicate data and we only need to return the reference back to the user. However, now let's consider a scenario where a unique data comes into the Minayo bucket. Now, Kafka will perform the same and notify Sanity controller about the new data. Sanity controller would compute the checksum of the content of the data and check that checksum in CouchDB. Now, since the data is unique, there would be no checksum present corresponding to the function hash. Hence, we can conclude that the data is unique. Hence, the data is passed with a stateless function to the serverless platform, and the output is computed. This output is then stored in one of the buckets in Minayo. The reference for that output is then stored corresponding to the hash of the input in CouchDB. Now let's have a look at the schema of our CouchDB database. So this is what a schema looks like. As mentioned, we are first computing the hash of the entire function code. This enables us to handle a situation where in the future, if the code of the function changes, a new hash would be computed. Then we compute the hash of the content of the data. Using this, we'll be able to conclude whether the data is unique or duplicate. If the data was unique, OpenWhisk will compute the output and this output is then stored in Minayo. The reference for that output is then stored corresponding to this hash. Now let's see how the user interacts with the Sanity framework. A user will first create a function. He then deploys this function to our serverless platform, which is OpenWhisk. Then, in order to use this function, the user runs the following command. Now, the input bucket, the output bucket, the name of the function, and the username is passed in this command. When this command is fired, our Sanity framework is started. The Sanity controller knows the location of the input bucket, the location of the output bucket, and it is waiting for the data to arrive. As soon as the data arrives in Minayo, Kafka notifies the Sanity controller about the data. The Sanity controller then computes the checksum of the data. Based on this checksum, we can conclude that whether the data is unique. If it is unique, then the stateless function is executed on OpenWhisk. If the data is duplicate, the output reference is returned to the user. Now let's have a look at some of the use cases that we implemented. We implemented the generation of an image thumbnail, analysis of the weather data, and counting the word frequency in a particular document as a part of this project. Now let's have a quick demo about how things work in our Sanity framework. So for this project, we have made use of two servers. On one of the servers, we have the OpenWhisk running. On the other server, we have the Sanity framework. Both of these servers were provided to us by our IBM mentor, and they are running in the IBM cloud. Now let's try and execute one of the use cases. Let's try and execute the image thumbnail use case. So now the first thing we need to do is we need to start the CLI for the Sanity framework. Now here I'm specifying the name of the input bucket. Let's call it test1. Let's call our output bucket test2. And for demo purposes, I've already created a dummy function that generates the thumbnail. I've named the function sprint. Let's give this a new username as sprint user. Now as you can see, the Sanity CLI has started. Now let's copy one of the image files in our input bucket, which is test1. So this is the command line interface that is provided by Minayo. So I already have an image as 1.jpg in one of my folders. So let's copy this to test1. My Minayo is an alias that I'm using to interact with the location of my Minayo server. Now the image has been copied. Here we can see that the action sprint has been invoked successfully. Our framework tells us that the data was unique and the output file was stored in the test2 bucket as 1-thumbnail.jpg. This whole process took about 0.2 seconds to execute. Now let's check our Minayo bucket. Let's see test1. Here we have the input 1.jpg. If you have a look at the size, it's about a 75 KB file. Now this is our output 1-thumbnail.jpg. If you look at the size, it's 1.42 KB. Now let's have a look if our new user was created in CouchDB. Here you can see that the sprint user was created in CouchDB. This is the unique document hash that was generated for this user. Now if we go to the users database, we can see that for this particular user, the output is stored corresponding to the hash of the input. Now let's try to send duplicate data to the same bucket. Let's say I rename my 1.jpg to 2.jpg. Now remember, the data is the same, only the name has changed. Now let's copy the 2.jpg to our input bucket, which is test1. The image has been copied. Let's have a look at the Sanity framework. So here we can see that the Sanity framework has detected that it's a duplicate data. Rather than computing the output, it just returned the output file reference, which is test2/1thumbnail.jpg. As you can see, the total time for execution is 0.03 seconds, which is much less as compared to the case where the unique data came in. Now, if we check the Minayo bucket, we can see that 2.jpg came in. But if we have a look at test2, there is no duplicate output that is stored. Even here we can see that for this particular user, there is no duplicate output reference that has been created. Hence, we are able to conclude that our Sanity framework is able to successfully deduplicate the function executions. In the demo, I illustrated how we could deduplicate the execution of cloud functions using the image thumbnail use case. But that is not the only use case that we implemented. We implemented a weather data use case which made use of JSON data. We implemented a word count use case which made use of text data, and many more use cases. These use cases illustrated that our framework has been generalized for different types of input data. Our journey so far has been like this. Starting with Sprint 1, we first begin with familiarizing ourselves with the serverless technology. We explored the various building blocks which could be used for our project. In Sprint 2, we set up all the components to interact with each other so that we could develop our framework. We learned how Kafka, which is a log processing agent, can be used as a message bus in order to trigger our controller when a put event happens in the Minayo buckets. Minayo, which is a cloud object storage, provided a very user-friendly APIs which was used in our project. CouchDB is a database technology which served very useful because we could add the schema of the database as a JSON file. And finally, OpenWhisk, which is an open source serverless technology. Sprint 3 was one of our major milestones because we were able to deploy all these components in containers in one of the VMs in IBM Cloud. We could then successfully able to deduplicate execution of cloud functions with the help of the image thumbnail use case. In Sprint 4, we generalized our framework by implementing different use cases, and we thought it would be really nice for the end user to have a CLI to interact with our framework. Hence, we began the design of our CLI. In Sprint 5, we designed and developed a database to handle multiple users. We realized this while developing our CLI that it should be robust enough to handle multiple users. And finally, we demonstrated the efficiency of deduplication when it comes to execution of cloud functions. During benchmarking, we found that most of our use cases took about 0.2 seconds for execution when the input data was passed to our framework. However, in the case of duplicate data, these function executions almost took a tenth of the time. Now considering the IBM Cloud, who charges these many dollars for a single execution of a function per second, imagine that the same function is executed 1 million times. It would cost about $2, which is a really small number for a single function execution. But now imagine if this function execution scales on a global level. In that case, we will be able to save a lot of money. Apart from the money that is saved from the function execution, we will also be able to save a lot of resources, network bandwidth, network costs, and round-trip executions. Now let's take a look at some of the numbers. Suppose if a user is computing the thumbnail of an image for every minute throughout the day, and this is done for 1,000 users. Now, if we consider for a week's time, that would lead to about these many number of function executions. But with the help of Sanity, we would be able to save 6 days worth of function executions. Since the user is sending only new data for the first day of the week, we consider that for the remainder of the week, he'll be sending duplicate data. This would mean that theoretically, the Sanity framework would be able to save 85% of the function executions. Some of the major takeaways from this project were that we learned to work in a team, and most importantly, we learned to develop software using the Agile methodology, Scrum in particular. Other learnings include we learned the internal working of the serverless platform, OpenWhisk in particular, working of Kafka and Minayo, how to make two servers interact in a cloud environment, building Docker images, how to make and set up Docker containers to interact with each other. One of the major learnings was how do we interact and communicate with the open source community and learned how the community works. When developing the CouchDB, we got to know about the architecture of CouchDB. The project was a great learning curve for us as it exposed us to real problems in the cloud and how we could tackle it. Now we know where to start and how to proceed when a problem is given to us. Some of the limitations of the Sanity framework are Sanity is not able to handle multiple threads or multiple requests. Authorization and authentication of users is still not supported, and there are no proper metrics or benchmarks for our framework where we could test the framework in a practical use case. So the future scope for our project would include user authentication, support for multi-threading, perform benchmarking at scale, generalizing framework to support multiple serverless platforms, and collect evaluation results and possibly write a research paper to support this framework. Thank you. Hello and welcome to the course project presentation for cloud computing.